Question number 8, we have a geometric, it says that a geometric progression is first term A, common ratio R and sum to infinity S. Second geometric progression has first term A, common ratio capital R and sum to infinity 2S. So we have to prove that R is equals to 2 capital R minus 1. Now to go about these questions, we can just start off by writing the formula for sum to infinity, which is A is the sum to infinity is equals to A upon 1 minus R. Now the sum to infinity for the second progression is A upon 1 minus 2R, and it is twice the first, this is basically 2 times the first progression. So to equate these two equations, what we have to understand is that as this is twice of the first progression, if I so let's take an example. So if this is 2, this is 4. Now to make them equal, I will have to multiply this by 2, and then they will become equal. So I'll write A upon 1 minus R and multiply this by 2 and write the other progression as it is, which is 1 minus. So this, okay, so there's a slight mistake over here. This should be a capital R, 1 minus R. So this will become A upon 1 minus R. So A and A will cancel out. Now cross multiplying, I have 2 minus 2R is equals to 1 minus R. So making this small r our subject, we get R is equals to 1 minus 2 plus 2R. So R is equals to 2R minus 1. So the first part is done. In the second part, it is saying that a third progression is equal to the second term of the second progression. Is equal to second term of the second progression. So we can write it as the third. It is now given that the third term of a first progression. So the third term of the first progression would be AR3 minus 1, because it's a geometric progression. So the formula for the nth term is AR power n minus 1. And it is equal to the second term of the second progression. So the second progression, second term would be AR into 2 minus 1, which would become A to the power R. So as they are equal, I can write AR squared is equals to AR. The A and A will cancel. So we have R squared is equals to R. So to solve this, we can use the substitution from the first part, which is that small r is equals to 2 multiplied by capital R minus 1. So in place of R squared, we can write 2R minus 1 whole squared is equals to R. Now solving this, we get 4R squared minus 4R plus 1 minus R is equal to 0. So this is 4R squared. 4R squared minus 5R plus 1 is equals to 0. Solving this, we get 4R minus 1 and R minus 1 is equals to 0. So we have R is equals to 1 upon 4 and R is equals to 1. Now as R cannot be equal to 1, since if R is equals to 1, there will be no progression, it will remain as it is. So we'll be taking R is equals to 1 upon 4. And now using the formula for sum to infinity, which is S is equals to A upon 1 minus R. Basically, we have to express S in terms of A. So we have to replace, first of all, this 1 minus R with 2R minus 1, and we get S is equals to A upon, so 1 minus minus 1 will become 2 minus 2R. And now the value of this capital R is 1 upon 4. So we'll write A upon 2 minus 2 into 1 upon 4. So we get A upon 2 minus 1 upon 2. So 2 minus 1 upon 2 is 3 upon 2. So this can be written as S is equals to 2 upon 3A.